Hello and welcome to Classes with Atish. Today we'll start a new series on waves. This lecture will be an introduction to waves. We'll go over classification of waves and end up with the general equation of a wave. So let's get started. So what is a wave? Wave is a disturbance. Disturbance from what? Disturbance from an equilibrium position. And this disturbance, when it travels over time, then a wave is formed. Okay, so let's say wave is a disturbance from equilibrium position that travels. Okay, now I'll underline a few things. Disturbance, equilibrium position, travels. What is a disturbance? A disturbance could be, let's imagine, let us imagine I have a wall and I've attached a string, okay, to the wall. This is the free end. I'm holding the string and then I'm creating a bump or a disturbance on the string. So what will happen after a while, there is a bump created like this, okay. The bump does not stay there. After some more time, it has moved across, it has traveled. And after some more time, the bump would have moved a little bit further. Okay, so I can say the particle that was originally here, now it has disturbed and it has a displacement up here. Okay, so the disturbance can be a displacement in this example. Okay, but it does not stay like that. It comes back to its equilibrium position. So what is the equilibrium position? This is the equilibrium position. And there was a disturbance from the equilibrium position, and then it came back to its equilibrium position. But the disturbance did not stay there. It moved around. So which means there was a particle which was at equilibrium position at this time, but here now we have a displacement of that particle from the equilibrium position. So is the particle moving? No, the particle 1 here is still here, right? The particle 2 or point 2 here is still at the same point. Particle is not moving, but the wave is moving. Okay, so that is the definition. Wave is a disturbance. A disturbance in this example is a displacement from mean position. So disturbance from equilibrium position, and the disturbance is traveling. The particle is not traveling. Okay. Now in this example, the particle is not traveling, but is the particle moving? Yes, the particle is moving. Particle is oscillating. What is the definition of oscillation? Oscillation means movement about a mean position. So it moves from the mean position. If this is the mean position, it moves up, then comes back to its mean position, moves down, comes back to its mean position. So that is one oscillation. Now this particle may oscillate in a direction which is perpendicular to the direction of movement of the wave, because the wave is moving this way. Or we might have a situation when the particles are oscillating in this direction and the wave is also moving in this direction. Depending on the way the particles are oscillating, we call this as transverse wave. If the movement of the particle is perpendicular to the direction of movement of the wave, and if the particle is moving along the direction of movement of the wave, then this is called a longitudinal wave. Okay, all right, so back to wave. So what exactly is moving? So wave is traveling, but what is it? What is traveling? So we can actually say it is energy that is traveling. Okay, let's also take a deeper look at what a disturbance could be. A disturbance can be a displacement, like we showed in this example of a wave traveling in a string. So displacement from equilibrium position, or it can be pressure differences or pressure variations, like in the example of sound waves, or it could be density variations, which could again be in sound waves or even waves in water, or it could also be disturbances of electric field and magnetic field variations in the case of electromagnetic waves or light waves. Okay, so disturbance can be anything. So don't just confuse disturbance as only displacement. It can be disturbance in pressure, density, or even electric and magnetic fields. Okay. Now, one way of classifying waves we call transverse and longitudinal waves depending on which direction the particles are oscillating. There is another classification based on medium. So if a wave needs a medium to travel, it's called mechanical wave. Sound waves, wave on a string, these are examples of mechanical waves. If a wave does not need a medium to travel, then they are called non-mechanical waves. Medium is not needed. Like light waves, okay, or electromagnetic waves. There is a third type of wave which we will not discuss in today's lecture. These are called matter waves. So this concept comes from quantum physics. Like if you have read about de Broglie waves, like subatomic particles like electrons, they behave as particles as well as waves. So those are called matter waves. But we'll not discuss this part of this particular lecture. Okay. So waves can be classified based on medium. Waves can also be classified based on direction of particles oscillating with respect to the direction of wave movement. So transverse and longitudinal waves. Now, I did mention that particle oscillation, but this you can replace with pressure variations happening in a direction perpendicular to the direction in which the wave travels, or density variations, or even electric and magnetic field variations. For example, you might be familiar with electromagnetic waves. So how electromagnetic waves work is we have an electric field which has some variations. Let's say this is the electric field variations happening. And then, so this is happening in, let's say, the z coordinate, this is the y, and this is the x. Okay. In the y coordinate, let's say the magnetic fields are varying. Okay. So electric field variations happening in the z direction, magnetic field variations happening in the y direction, but the wave is propagating which direction? The x direction. So wave propagation is both perpendicular to variations in the electric field as well as perpendicular to the variations in magnetic field. So electromagnetic waves are actually a example of transverse waves, okay, because the variations are happening perpendicular to the direction of the wave traveling. Okay, longitudinal waves could be sound waves. Ripples in water, they are a combination of longitudinal and transverse waves because both type of variations can happen. The particles oscillate about a equilibrium position up and down, as well as there could be water density differences as the ripples move out from the center. Okay. So this is an introduction of waves and the classifications, two ways how we classify waves. And now we will look into detail about these disturbances, how we can represent a wave in the form of a wave equation. Okay. So our goal is to write the general equation of a wave. Now since wave is a disturbance, we will write the equation of the disturbance. Now what could be this disturbance? This disturbance can be displacement from mean position, or it could be change in density, or it could be change in pressure, or even changes in electric and magnetic fields. Any disturbance that travels over time is a wave. So let's say this disturbance we denote by y. Okay? Just so we can understand this clearly, visualize this, let's take an example of a wave on a string. Okay, so let's say this is my x and y coordinate. So this is my y coordinate, this is my x coordinate, and the string is fixed to a wall. Okay, and I am creating some waves on the string. So let's say the string is like this. Okay. So if we look closely, the particles on the string, they had a displacement from the mean position. Okay. So our goal is to find out the displacement, which is y, from mean position along any point on the string. So if at a distance x, I want to find out what is the displacement, that should be obtained from the general equation of the wave. Okay, so let's say if at a different x, let's say this is x1, this is x2, at a different x, this will be the displacement. Okay, so if we can find out some way to represent this displacement y for any x along the length of the string, also there is another factor at any time, then we have the equation of a wave. So if I ask you what is the displacement of the string, you will say that that question is incomplete. Tell me at which point on the string we are looking at displacement. So if I tell you at x2 distance from the origin, what's the displacement? You would still say that that question is still incomplete, because you also need to specify at what time I am looking at this displacement. Because with time, the wave is moving. Let's say if I take a snapshot at t1, it looks like this, but snapshot at t2 might be like this. Okay, so if I then consider the displacement at x2, which is this distance, the displacement, this y2 can very well be different from this y2. Similarly, at x equals x1, let's say here is x1, this y1 is different than what y1 we had at snapshot t1 time, right? Because the wave is moving. This crest has now moved along. This crest has moved along, okay? All right. So then we realize that y is not only a function of x, but it is also a function of time. Okay. Now, before I go into a little bit depth here, let's just consider any one particle. Let's just consider this particle, which is at x equals x1. Okay, the same particle at a different time. Now, if I just focus on this particle, how is that particle moving? At some time, it was in the mean position. So, if I redraw the coordinates, okay, at some time it was at mean position, and then it started to move up. It reached a certain height, then it went down, came back to its mean position, reached a certain height here, and then it came back. So if I just focus on that particle itself is oscillating about a mean position. That oscillation may be a SHM, simple harmonic motion, or may not be, okay? But if you focus on every point on the string, every one of them are oscillating about their mean positions. Let's for a moment assume every one of these particles are performing simple harmonic motion. These particles are where they are not moving, the wave is moving, but each particle is performing a simple harmonic motion. So we can also say a wave is a collection of simple harmonic motions. It is not one simple harmonic motion, it is a collection of simple harmonic motions where each and every particle on the string are performing the same simple harmonic motion. If we generalize it, we can say the same oscillation. Okay? Let me write that down. Each particle is performing oscillations. Okay? Wave is a collection of oscillations of each particle, or we can write oscillation of every particle. Now in this case I am writing it's an oscillation of every particle because we took the example of a wave on a string. If I generalize this, we can say wave is a collection of oscillations of disturbances. These oscillations can be any disturbance, not just a displacement. All right? Okay. So we achieved something here. So we found out that y, which is the displacement in this case of any particle on the string, is a function of the position on the string and time. Now, if we know this, can we say any function of y is then a wave? Can we say y equals 2x square plus 3t is a wave? Or maybe y equals x by t plus 3t square. Is this a wave? No. These are not waves. Why? Because we have to satisfy certain conditions for an equation, for a function of x and t to be a wave. What are those conditions? Let me write them here. The conditions are, there are two conditions. One is the partial derivative del square y del t square should be equal to some constant k del square y del x square, where k is a constant and k is not equal to 0. This is condition number 1. Okay. Condition number 2 is y should be defined for all x and t. Both these conditions are very, very important. Okay. This condition is actually a partial differential equation. When we solve that partial differential equation, we would get a solution which would be the general equation of a wave. But conversely, you can also look at any function and apply these conditions and see if it is a wave. So for example, let's take up this particular. Del y del t square. Del y del t is what? Is 3. So and del square y del t square is 0. Okay. Del y del x is how much? 4x. So del y del x is 4x. Del square y del x square will be 4. Is this satisfied? Only way this is satisfied if k is equals to 0. So therefore, this is not a wave. How about this? Even before I do number 1, I can see that y is not defined for t equals 0. So therefore, this cannot be a wave either. What equation can be a wave? Let's look at that. Say for example, we have a equation y equals a sine at plus bx. Okay, let's compute number 1 for this equation. Del y del t will be y. Let's write those steps now. Del y del t will be, so sine becomes cos at plus bx, and this will become aa. This a comes out. Okay. And then if we do del square y del t square, this becomes what? Cos becomes minus sine. So minus aa we had sine at plus bx. But we also differentiated one more time. So a square. Now let's do del y del x is how much? It will be ba cos at plus bx, and del square y del x square will be how much? It will be minus b square a sine at plus bx. Now if I divide this by this, so we are dividing this by this. So what's the value of k? Sine gets cancelled out, minus minus and a gets cancelled out. It becomes a square by b square. Given a and b are not equals to 0, is k a constant? Yes, and this is not equals to 0. So therefore, this condition is satisfied. Now is y defined for all x and t? Sine of any value lies between minus 1 and 1. So therefore, it's defined for all t and x. So this condition is also satisfied. So therefore, this is a wave. Okay. Now, in general, if there is any function given, to find out if it is a wave, we need not do all of this all the time. The generic solution of this partial differential equation is if y is of the form ax plus bt, where a and b are not equals to 0, then that would be a solution of this, and therefore that will be a wave function. You can also write ax plus minus bt. Okay. In addition to this form, also always check. What should we check? That y is defined for all values of x and t. Don't forget this step. This is also important. Okay. So maybe you can take a look and tell me which of these functions represent a wave equation. Y equals log x plus 3t, y equals e to the power minus 3x plus 4t, y equals 3x plus 5t, and y equals 2 by 3x plus t square plus 4. Okay, so let's check first. Is this one of the form this? Absolutely. But is y defined for all values of x and t? What about x plus 3t if that is negative? Then it's not defined. So this is not a wave. Okay. Is this of the form function of ax plus minus bt? Yes, it's ax plus bt. Okay. So this is satisfied. Is y defined for all values of x and t? If minus 3x plus 4t tends to 0, then this becomes 1 by e to the power 0, then this will tend to 1. If this tends to a very big number, then it becomes 1 by e to the power infinity, then y will tend to 0. So it is actually defined for all values of x and t. So this is a wave function. Is this a wave function? It might look like this. It is actually of the form f of ax plus bt, but for as time increases, as t tends to infinity, y tends to infinity. So y is not defined for long times. So this is not a wave. Is this a wave? Here, only thing we have to consider is, can the denominator be ever 0? This is a positive number, this is a positive number. So it cannot be 0 for any x and t. Okay? So, and this is of the form ax plus bt. So this is a wave function. Okay? So that is how you are gonna check which is a equation of a wave and which ones aren't. Okay? Okay. So far we figured the general equation of a wave is of the form y equals f of ax plus minus bt, okay, where a and b are constants, okay, and y should be defined for all x and t, okay. Now, just from this expression, can we also find out what is this velocity of a wave? Yes. Velocity of the wave, or the velocity of the disturbance moving, this is not the velocity of the particle oscillating, okay? This is the velocity of the disturbance moving, or velocity of the energy moving. This is given by coefficient of t, coefficient of time, divided by coefficient of x. So in our example, this will be b by a. Okay, so the velocity of a wave, usually denoted by a small v, is b by a. Okay, and in which direction is the wave moving? If a and b are of same sign, then the wave is moving in negative x direction. Okay. If a and b are of opposite signs, then wave is moving in the positive x direction. So we can say, if it is of the form ax plus bt, let's say a and b are both positive constants, okay, then this one is moving in the negative x direction. Similarly, if we have minus ax minus bt, then also it's moving in the negative x direction. Now if we have ax minus bt or minus ax plus bt, then these are moving in the positive x direction. Okay? Okay, let's take an example. Let's say we have y equals 4 by x minus t square plus 2. Okay, is it of this form? Y is a function of ax plus bt? Yes. Is y defined for all x and t? Yes, because the denominator can never be 0, right? So y is a wave. Now if I say what is the wave velocity of this wave? Wave velocity will be coefficient of t is 1, coefficient of x is 1. So 1, whatever units, maybe meter per second if we are assuming all SI units. But this one has both have opposite directions, both have opposite signs, so moving in positive x direction. Okay. Now if I ask you what is the amplitude of this wave? What is amplitude? Amplitude is nothing but the maximum displacement of a particle. So if I can find y max, then I can find amplitude. How do I find y max? Y will be maximum when the denominator will be minimum. What is the minimum value of the denominator when x equals t? So this will be 0. So 4 by 2. So 2 units is the amplitude. So that's how you find out y amplitude of a wave. Okay. Okay. Another example. Y equals 4 sine 2x minus 3t. What is the wave velocity? Wave velocity is coefficient of t divided by coefficient of x, so 1.5 meter per second, let's say. And this is moving where? In the positive x direction, because these have opposite signs. What is the amplitude of this wave? Amplitude is maximum value of y. What is y max? When sine of anything is maximum, what is maximum value of sine is 1. So this is 4 meters. Maybe I should also write the units here, meter per second, meter. Okay. So pretty easy. In the next lecture, we will talk about a specific wave, which is the plane progressive harmonic wave. So the plane progressive harmonic wave is when every particle on that wave executes a simple harmonic motion, or every disturbance on that wave executes a simple harmonic motion. And we'll see what is the generic equation of a plane progressive harmonic wave and do a little bit of more details around that. Okay, so see you in the next one.